the last time we looked at deuterium coupling, which was different from what we're used to because deuterium has a spin of 1. So this lecture I'm going to look at some boron spectra to show you the coupling of it, and then we'll move on to some dynamic stuff. So this is a proton spectrum, so a proton can potentially couple to anything it is connected to, in this case boron 11 or boron period. And but the squiggle brackets here mean that we are decoupling boron 11. So all you see here is straight proton-proton coupling, if that even happens, but all of these signals here are singlets. Also a reminder, boron is 80% abundant. Its spin is 3/2. That's just for later. And then 20% is the other isotope, which is boron 10. And it actually has a spin of 3. So we do have the potential of coupling to boron 10 because we're only decoupling boron 11 here. So keep that in mind. So this is our carborane. No, not a carborane. It's just a borane. Boron hydrogen containing compounds are boranes. We already know about the 3 center 2 electron rule, so we can have some bridging hydrogens and terminal hydrogens. And so each of these borons here are labeled, and the signals here are for the hydrogens, of course, that are connected to those borons. So for example, 3 and 1 are equivalent. That means these two hydrogens would show up together, and I've labeled that here, 3 and 1. That would be this signal, and so you can kind of see that here. 2 and 4 are together, and then these 4 are all chemically equivalent. They show up here for another singlet, and then we also have those bridging hydrogens, which are here. Here they are bridging. I almost colored the wrong one. It's not all that important because I don't want to look at the symmetry and you to be able to assign an NMR spectrum. I just want you to realize that, okay, we have 1, 2, 3, 4, 5 chemical environments. They're all singlets, and then if we actually just run a pure proton and we zoom in on one of these signals here, so we're going to zoom in on 2. This is what it would be looking like as decoupled. And here we have a proton NMR that's not decoupled. So once again, if we look at the spectrum here, that's 1 boron, 2. This hydrogen is connected to 1 boron, so 1 nucleus. So 2Ni plus 1, it would be 1 nucleus. Spin equals 3/2 plus 1, so that gives me 4. Okay, and that's exactly what we see. We see a quartet, and they are roughly the same height. So it's not this quartet that we use for Pascal's triangle, because it's a single signal once again. Now, the cool part is that I'm guessing that the signals here, which could be an impurity, but I'm guessing it might actually be boron 11, because boron 11 would give you rise to a heptet or a septet, right? Because boron 11 would have a spin of 3. So 2 times 3, 6 plus 1 would be 7. So that would actually be a heptet, and we would expect that to be 1, 2, 3, 4, 5, 6, 7 of equal height. And since it's 20% abundant, I'm guessing that's what we're seeing here. So just to show you that if this nucleus is anything other than spin 1/2, that you have to use the formula to determine what that spectrum is. Okay, so let's look at some crazy stuff here, right? So this is a simple borane compound. We have, and it shows you each nucleus that splits the proton. So this is a proton NMR, and so it's labeled 1 signal. This is all 1 signal, HT. So this is that bridging, that's that terminal hydrogen here, right? So we have HT and we have HB. So we're looking at the terminal hydrogen here, and so they can be coupled to boron, but they can also be coupled by 2 bridging hydrogen. So the strongest coupling would be to that boron Ba here, right? So the first thing we see is that hydrogen gets split by one nucleus of spin 1/2, not 1/2, I is equal to 3/2. That would be the strongest splitting, and so it splits that into a quartet. So that's what this is. And then the next strongest coupling is actually not the closest one, which are the two bridging hydrogen. It's the larger nucleus, and that also makes sense, right? We have more, we have a heavier nucleus, and so it's going to cause, even though it is further away. And as I said, I would indicate that, I would tell you that JHT to JBA is larger than JHT to J. I don't want to drag this out. The HB, and then finally the hydrogen coupling would be the weakest, and I mean that's not all that important right now. But again, it's a single nucleus, right? And so we see another quartet. So we already have a quartet of quartets. And then each of these lines is actually split by two hydrogens, which has spin 1/2, so into a triplet. So this is when each of these little quartets of quartets splits into this humongous, and you can actually see that it's not just theory. Here's an actual spectrum. This is a little different. See, this one had methyl groups, which made the bridging and the terminal hydrogens inequivalent. But here we have we have 4 terminal hydrogens and 2 bridging hydrogens, and they should be chemically equivalent. So all of the HTs and HBs, and that's going to cause a different splitting pattern. So we can do that. This one isn't as clean here. The terminal hydrogens, which are clearly split by a boron here first, and so this is your quartet. That's rather large, and then each of these, it's kind of messy. It doesn't look like you can figure this out much, but it's also going to be split by the bridging borons here. If we look at bridging hydrogens, of course, if we look at the signal for the hydrogen that's bridged, the 2 of them, so that's one signal. You actually have 2 equivalent A and B. They're chemically equivalent. That's 2 nuclei that these are split by. So then the 2 times N is going to be, just in case you forgot, 2 Ni plus 1. No, N is going to be equal to 2. I is still 3/2, and then plus 1, that would be 2 times 2 times 6 plus 1, that would be 7. So it would be a septet, and that's exactly what we see. That's this larger splitting here. This is going to be those 7 signals, 2, 3, 4, 5, 6, 7. That's your heptet. And then each of those is then further split by 4 hydrogens, right? That's spin 1/2, so we see pentets, right? So 1, 2, 3, 4, 5. So this heptet gets split into pentets. So the signal we see for the bridging hydrogen is a septet of pentets. Okay, all pretty fascinating, right? This is an example for a phosphorus 31 NMR, and so the splitting of phosphorus is 1/2, and then the other nuclei that are potentially going to cause any splitting is the hydrogen here. The hydrogen also has a spin, as we know, of 1/2, so both phosphorus and hydrogen will cause that. That's pretty simple and straightforward, and so we have these 2 metals, manganese and palladium. They are bridged by a phosphine group and a hydrogen bridge. And so the chemical environment here, or the geometry of palladium, is square planar. So we have cis and trans phosphine groups. And if we are to look, let's say it's signal C, which is this one, we're going to expect splitting by 2 other phosphorus. So B and A are going to split this into doublet of doublets, and we would normally not expect the coupling strength, or J, to be drastically larger, but it turns out that the trans groups will cause a much stronger splitting than the cis groups, and that's despite the fact that we're just 2 bonds removed, right? So we have 1, 2 bonds to this phosphorus and 1, 2 bonds to the other phosphorus. But it's the trans that's going to cause a much larger splitting. So the phosphine here, the phosphorus from the trans group, is going to cause this rather large splitting here, which is much larger than the shorter, or not shorter, the cis group, which is just as far away, but it's in the cis position, so it causes a much smaller splitting. So the 2 phosphorus are going to split this group C into a doublet of doublets. All right. And then, of course, the hydrogen is a much smaller nuclei. It's also going to cause a little bit of a splitting, but it's going to be much weaker. So that's what the smallest splitting is the hydrogen phosphorus coupling. This is the cis coupling, and then the long one here is the trans-trans coupling. We can also take a look at the other 2 signals, but the only point of this slide here is to look at cis versus trans coupling of square planar complexes. So keep that in mind. That can be another helpful tool to elucidate the structure of some compounds. All right, so let's come back to those 6 examples that I showed. We already established the number of signals, and next we're going to look at splitting. So once again, I think you should pause, see if you can figure it out yourself, and then when you come back, I'm going to go through this rather quickly. So we have 2 groups. Let's label this A and then B. And so we have 2 signals, and fluorine, these were all fluorine NMR. Fluorine has a spin of 1/2. So we simply have 2 triplets, right? So A is going to be split by 2 other nuclei into a triplet, and the same is true for signal B. So A and B will look like that. So 2 triplets. This one here, we have a single signal, so that's just going to be a singlet, right? They don't couple each other, they're chemically equivalent. Here we also have 2 signals, but we have A and B, and so A is going to be split by 1 other nucleus into a doublet. All right, so this is signal A, and then B is going to be split by 2 nuclei, the 2 A's, into a triplet. All right, and you can try to make, when you draw these, you can try to make them follow Pascal's triangle, but you know, I'm not the greatest of following that. As long as I see a triplet, as long as a triplet doesn't look like this, which that would be a single nucleus, like with a spin 1. Okay, so those are the 3. Let's move on to the next ones. Here we also have the circles are going to be A, and then this is going to be B. And so we see a very similar pattern here. A is going to be split into by 1 phosphorus into a doublet, and then B is going to be a triplet like this. Done. And so now we are introducing a second active nucleus here. So if we did a fluorine NMR, so 19F NMR, if I do tell you that the spin of phosphorus is equal to 1/2 and the spin of fluorine is equal to 1/2, you want to consider the both of the splittings. All right, so first of all, it's fluorine NMR, so we will label the 2 groups. So this is going to be A, and this is going to be B. Now, this gets a little tricky because of cis and trans coupling, but I'm not going to look for a super detailed, accurate splitting diagram, but I might tell you what the splitting is, right? So I'm going to say that JFF is smaller than JFP. And so what you should do is, as you go through this, you should go with, whether it's cis or trans, I'm not distinguishing here. So if this is all of the information I give you, you can take a look at, let's say, signal B here. So you start with B, and so you want to use the stronger coupling first. So the phosphorus is going to be splitting this into a doublet. So you can kind of do that. And then the weaker fluorine here is going to split. There are two groups, so that's going to be a triplet. So it's going to be a doublet of triplets. So then you just take that and turn it into a doublet of triplets. You know, you can straight get to that it's a doublet of triplets, but if you do this step by step, it might help you to draw this doublet first and then turn each of these doublets into a triplet. So this would be signal B, and then signal A. Now we have, again, we are going to use the fluorine phosphorus coupling first, which is also a doublet. I'm going to run out of space for this last one here, but I'll manage somehow. So this is still this one here. And so, and then we have, for signal A, we have only one other fluorine, so it's just going to be a doublet of doublets, right? So we have two nuclei that are going to split this signal A into a doublet of doublets. This last one here, let's say A, and then B, 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 B. Let me do some magic. So here we have two signals. A is going to be split by 4 other nuclei into a pentet. 2, 3, 4, 5. And then B is just going to be a doublet. All right. So making a lot of progress already. We know about coupling, and we know about number of signals and symmetry. So this comes straight from a quiz I gave a couple years ago. I asked to predict or sketch the NMR spectra for the following 5 compounds. And so I'm going to work the top 3 in this lecture and then the other 2 in the next lecture, just so it doesn't get too long. But I would highly recommend, once again, for you to pause and see if you can do this yourself. So the first one here is a proton NMR. All right, so we're going to label protons. So we have a trigonal bipyramid. Those are 2 different positions, axial and equatorial. I'll just go A and B. So now we know how many signals to expect. We expect 2 signals. And then we don't have to worry about silicon coupling. That's what the squiggly thingy means here. We don't worry about it. And so there's only coupling to other hydrogens. And then I will always give you the nuclear spin of the nuclei involved. So even if I didn't indicate that this was silicon-29 decoupled, if I don't give you the nuclear spin of silicon-29, then you can ignore potential coupling to it. So all we have is 2 signals. Let's start with A. A is going to be split by 3 other hydrogens. So that's going to be a quartet. That would be A. And then B is going to be a triplet because it's coupled to the other 2 nuclei here, right? It's N+1 rule, and so that's all it is. Here we have a fluorine NMR now, and we are going to ignore hydrogen, right? Because of the squiggle brackets. I know there's a name for it, I just don't remember what it is. Of course, I'm an immigrant, so I have an excuse. Anyway, so we're doing fluorine NMR. This is an octahedron, and so we have these 2 are chemically equivalent. So it's A and B. So we have 2 environments we're looking at. We can luckily ignore all of the hydrogens because that could make things complicated, because the hydrogens there's 2 different hydrogen environments. And I would also have to provide you with the coupling constant, the strength of the coupling constants, for you to be able to answer that. Although I do expect you to know that the fluorine hydrogen coupling is going to be much smaller than the fluorine-fluorine coupling, simply because it's a larger nucleus, right? Fluorine has a much larger nucleus and it's going to have a stronger splitting. So fluorine splitting would be much stronger than fluorine hydrogen splitting. But we're easing UN into this, so we're just going to look at the two different fluorine environments. So nothing really changes here. We just have signal A is going to be a doublet, and signal B is going to be a triplet, and we are done. So this next one is fluorine NMR. These are chemically equivalent, so these are both the same. So we just have one signal. However, I am telling you that this is going to couple to deuterium. And I give you a spin of iodine, of fluorine as well. But in this case, we don't have to worry about it because there is no second chemical environment. So this is just going to be split by deuterium. So it's actually not that hard. It's just one deuterium, which has a spin of 1. So we get a triplet, and they're all going to be equal height. Now you're lucky that I didn't say that boron has a spin, or boron 11 has a spin of 3/2. So consider yourself lucky. All right, so I think that's enough. We're going to come back in the second lecture. I'll do the other remaining patterns, and we're going to do some dynamic NMR, and we're done.